Cylinder deactivation is a system that deactivates individual or a group of cylinders during cruising or light throttle situations. These systems lower exhaust emissions and fuel usage by increasing the active cylinder's pumping efficiency. During cruising conditions, the ECM will increase the throttle valve angle, allowing more air to enter the active cylinders, therefore achieving higher volumetric efficiency. The injector fuel delivery to these cylinders will be increased due to this extra air. The end result is the active cylinders will work more efficiently. This equates to a lower fuel consumption and less exhaust emissions. The fuel delivery may be increased by means of increasing the active cylinder injector pulse width and/or by increasing the fuel rail pressure. A great example of this would be an 8-cylinder engine operating at cruise throttle with an injector pulse width of 4 milliseconds. This would equate to 32 milliseconds of injector duration for every 2 crankshaft revolutions. During cylinder deactivation, if the injector duration on the active cylinders was increased by 50%, we would still only have a total injector duration of 24 milliseconds per 2 crankshaft revolutions. Because of the greater cylinder efficiency and less fuel injected, we will achieve lower exhaust emissions and better fuel economy. Depending on the vehicle manufacturer, these systems may disable up to half the available cylinders. Cylinder deactivation isn't new technology. It has, however, been perfected over the years. The engines now have a much smoother transition between active and inactive modes. The main types of cylinder deactivation used on vehicles are overhead valve and overhead cam type. We'll be focusing on overhead valve type in this video. Components of the cylinder deactivation system will include the engine control module and associated components, communication bus, activation solenoids, and deactivation lifters. The engine control module is responsible for this system. It uses direct inputs including engine speed, coolant temperature, engine oil pressure and temperature, barometric pressure, engine load, accelerator pedal position, and throttle valve position. And indirect inputs from the communication bus such as brake pedal position, vehicle speed, and brake booster vacuum. Armed with this information, the ECM is then able to determine when to deactivate the appropriate cylinders. There is one output from the ECM for each control solenoid. These solenoids are electro-hydraulic actuators that are in the normally closed position. Each solenoid controls the application of engine oil pressure to the intake and exhaust valve lifters on the cylinders selected to deactivate. All 4 solenoids have a common supply from the ignition circuit. The control for each solenoid is via a low-side driver from the engine control module. The solenoids must be activated in the correct firing order to ensure a smooth transition. The deactivation lifters are located in the engine crankcase and are similar in appearance to a conventional hydraulic lifter. The deactivation lifter is constructed as an outer body, inner hydraulic lifter, an inlet port, locking pins and spring. There is also a mainspring that allows movement between the lifter and the outer body for noise reduction during cylinder deactivation. When cylinder deactivation is commanded, the ECM will determine the next cylinder in the firing order to be deactivated. Although both intake and exhaust valve lifters are controlled by the same solenoid, the intake and exhaust valves do not become deactivated at the same time. Cylinder deactivation is timed so that the cylinder is on an intake event. On the intake stroke, the exhaust lobe is on its base circle. relieving any force on the locking pins. The oil pressure applied via the deactivation solenoid can now retract the locking pins. The exhaust valve is now deactivated. The intake valve cannot deactivate until a deactivation lifter reaches the base circle of the camshaft lobe, reducing the force on the locking pins. Again, oil pressure from the control solenoid can retract the locking pins, deactivating the intake valve. The inner body can now move independently of the outer sleeve on both lifters. All cylinders can be deactivated within 2 crankshaft revolutions. Some systems may have separate deactivation solenoids for the intake and exhaust valves. Nevertheless, they will all deactivate the exhaust valve first. As each cylinder is mechanically deactivated, the ECM disables the fuel injectors for those cylinders. Ignition may remain active to help prevent spark plug fouling. Cylinder deactivation will only remain active for a pre-programmed time. The ECM may return to all cylinder mode for a short period before recommencing deactivation mode. On systems that can deactivate all cylinders, cycling may occur to prevent uneven cylinder wear. As the ECM deactivates each cylinder, the throttle valve angle is increased to maintain engine speed. This will also be combined with an increase in fuel injector duration and oil pressure change. With an increased air mass for each active cylinder, there will be an associated increase in cylinder pumping efficiency, thereby raising the dynamic compression ratio. The deactivated cylinders retain a fresh air charge that acts as an air spring. One piston will compress the air charge, while its opposite will be forced down the bore by the expanding air charge. These two forces will cancel each other out, resulting in a balanced reciprocating mass. When cylinder deactivation mode is no longer required, the ECM shuts the solenoids off, removing oil pressure from the locking pins. Remaining oil from the lifter body is exhausted to the crankcase via a port on the side of the lifter. As the cam rotates, the lifter body expands, aligning the locking pin to the locating holes. The pins are pushed into position via the expansion spring, locking the lifter body and sleeve once more. At the appropriate time in the crankshaft cycle, the ECM re-enables the fuel injectors for all cylinder mode operation. Cylinder deactivation may be inhibited for the following reasons. The engine coolant temperature may be out of its operating range, an incorrect transmission gear has been selected, or a gear shift is in progress. Accelerator pedal rate of application is too fast. The engine oil pressure and temperature is out of its range. Engine or vehicle speed is out of its operating range. Deceleration fuel cutoff is operating. A traction control event is occurring. Catalytic converter over temperature protection is active. All cylinder deactivation DTCs are present. For reliable operation of any type of hydraulic actuated cylinder deactivation system, the correct viscosity and type of oil must be used. As you can see, cylinder deactivation is a mechanically simple system with a complex control that must satisfy many parameters for efficient operation. Understanding how these systems work will help with your diagnosis and enable you to work on this complex system. Thanks for watching.